So we've done energy, just kind of relating it to what we have as far as types of energy goes. And then we did a pine cone falling from a tree, and we looked at that changing from potential energy to kinetic energy. And so now I want to bring us back to something that you've seen from the beginning of the quarter, and that is launching something at an angle, and we want to know its speed when it hits the ground. So here we go. Let's figure it out. The first thing I suggest that we do is that we label the types of energy we have at the different places that we're interested in. So we're starting off here, and that is at this height of 165 meters. So we definitely have potential energy related to height, and it's moving. So it has initial kinetic energy, so it has kinetic energy. Now, we only are interested in comparing height differences. So one of the things I like to point out is that it doesn't matter if all this is taking place on top of a 5,000 meter hill, where this is like the shorter peak of the two. When we're comparing energy, we're only looking at the beginning and the end snapshot. So I'm only interested in, I can call this a height of 0 and this a height of 165. I'm only interested in the potential difference for this height. I don't care anything about what's happening below it. So then the next spot I'm interested in is here. So if none of the height matters below, then the only thing I'm interested in here is what its kinetic energy is, because my comparison of height is that this is 0, so I have no potential energy relative to height here. And now I can turn this into an equation. We're going to say, okay, I'm starting with potential energy and with kinetic energy. We'll label that with a 1, and that's all going to go into this final kinetic energy. Cool. Now, we look at the 180 degrees and at the angle, and some of you might have some traumatic flashbacks of having to break everything into vectors, but not to worry. This is kind of the nice thing about working with energy, and we'll talk about the shortfalls of it after we finish this calculation. So let's just write this out. Potential energy, let's see, that's mgh. So this is my force, the force due to gravity, and this is the distance it's covering. And then plus kinetic energy, which is my 1/2 mv1 squared, equals my final kinetic energy, 1/2 mv2 squared. And now I can simplify this sum. I can look at this and say, okay, so what do I got? M's everywhere, so all my masses are going to cancel. And I can rewrite this as GH plus 1/2 V1 squared equals 1/2 V2 squared. Now the next thing I want to do is get rid of this 1/2, so I'm going to multiply both sides by 2. And I get 2GH plus V1 squared equals V2 squared. And I kind of feel like this looks familiar to me, because I look at this term here, and that G is acceleration, so I have 2 times acceleration, and this height, well, that's just a delta y. 2a delta y plus V naught squared equals V final squared. That feel familiar? Huh, imagine that. So masses cancel out because the acceleration due to gravity isn't dependent on the mass of the object. That's why we were able to do all this fancy stuff in the beginning without ever worrying about how massive something was. So now let's just simplify this further, that I'm going to take the square root, and I get 2GH plus V initial squared, and that equals my V final. So now we can put our numbers in. So here we go. 2 times 9.8 times my height of 165, 65, not 55, eraser would be helpful. 165 plus 180 squared. Leaving off the units just to leave things a little bit more compact. So let's see what we come up with here. And I get 188.77, or otherwise known as 189. Come on. 189. As soon as I can get my pen to work. There we go. 189 meters per second. Now some of you might be saying, well, on the exam that we took on kinematics, I lost points because I used the entire velocity and the acceleration. You lost points because you were using energy, not using kinematics. We didn't have a relationship with energy at that point in time. So why did that work out? Well, so first of all, this gives me my final speed. What this doesn't give me is the velocity in the y or the velocity in the x. If I wanted that, I would need to break this thing here, break this thing here into components, and then do the same things we were doing when we were doing projectile motion. In the end, I know that my x velocity would be the same, so then I would just need to determine what the y velocity is. So I don't have my components. I don't know how high I went, so I can't get a max height. I don't have a distance here that I've covered. So again, I would need to break that into pieces. And the last thing I don't have is like an angle of impact. So this is great for getting me the overall snapshot of what everything is, but it doesn't give me the fine details. But there's no angles. And one thing I want to point out here is that everything we're doing here, after we've taken it from its physical quantities, this is all scalar stuff. We don't have any vectors here. You notice the one thing I didn't do is throw in negative signs or ask you to define anything. And that's because, strictly speaking, when I do this step up here, I have defined what my heights and whatnot are. Where it would become important for you to define what's positive and negative is if you don't do this step, if you don't just look at before and after, and instead you do something like this, where you'll see like the change in potential energy is going to equal the change in kinetic energy. Because if I'm going to do that part, then I do need to be very careful with what my initials and finals are to have my signs correct. All right, there we go. On to the next.